Hello, this is Chris Mack, and I'm about to start a series of what I call bonus lectures, added lectures to my course on micro and nano fabrication that is already complete and online. Look at the web address at the top of the slide to see where that is if you haven't seen it before. But I'd like to add a few extra lectures that are not part of the regular course but are interesting, and the interested student may want to dive into a few of these extra topics should they spark their imagination. And one of these topics is mask making. So for the next 3 lectures, I'm going to talk about how photomasks are made. As I said, there's going to be 3 lectures in this series of the first 3 of our bonus lectures. And in the first one, we'll talk about what a photomask is and what the basic steps are in making a mask. We'll also talk about different kinds of photomasks, binary and phase shifting masks, and also reduction ratios. In part 2, we'll specifically focus on the writing step. We use e-beam lithography to write our masks, and it's a very interesting process. We'll talk about that in part 2. And finally, in part 3, we'll look at the other very important aspects of the mask making process, in particular inspection and repair metrology. And finally, at the end, we'll throw in some of the challenges of the new style of mask that people are starting to build, EUV masks, in the hope that EUV will soon be ready for manufacturing. So, where does the mask fit into the lithography process that's used for printing patterns on integrated circuits on wafers to make our chips? Well, the lithography process takes a wafer, coats it with a photoresist, and then puts it into this exposure tool, the stepper or the scanner. This exposure tool then has a photomask, a plate that has on it the patterns that we're trying to print on the wafer. Then it projects an image of that mask onto the wafer, exposes the resist-coated wafer. Those wafers come off and get baked and developed, etc. So what we're going to do is talk about this mask that gets inserted into the photolithography tool to project the images of the mask onto the wafer. Well, the mask is also called a reticle photomask in the world of optical lithography, but it has all these patterns that we're trying to print. It's made up of a transparent substrate that has opaque regions where we want to block the light, and it's transparent where we want the light to go through. The basic substrate is a standard size, 6 inches by 6 inches and a 1/4 inch thick. It has these opaque regions typically made of chrome or molybdenum silicide, and we're going to project the image of these chips onto the wafer. Typically the mask is 4x bigger than the patterns that we're trying to print on the wafer. There's also 1x steppers and 5x and 10x steppers, but the standard for state-of-the-art lithography is a step and scan system that uses a 4x reduction ratio. That means we can't fit an entire wafer's worth of pattern on the photomask. We can only fit some number, usually more than 1 chip. So for example, the picture here shows a mask that has 6 chips on it. Those 6 chips are completely identical, and then we print all 6 of them at once. When we focus down on the wafer, we step the wafer to a new location and print again. We also don't need just one mask because we have lots of lithography steps to build up all the patterns of transistors and isolation and metallization runs, contact holes that are used to make up these complicated integrated circuits. We need lots of photomasks, at least one for every lithography layer. Back 15, 20 years ago, when we were at the 180 nanometer node, we were making devices that needed about 25 masks. At the 32 nanometer node, our devices need closer to 50 masks, thereabouts. And today, our state-of-the-art 14, 16 nanometer node devices require something like 75 masks to make an integrated circuit. The masks are quite critical, as you might imagine, and they involve their own lithography process in making them. we have to use a different kind of lithography process than we actually use when printing the wafers with a photomask, because to make a mask, we don't have a starting mask. We have to make it from scratch. We begin with a mask blank. The mask blank is the substrate that already has the absorber films and the resist coated on it. Most mask makers don't make their own blanks. They actually buy these blanks from a third-party company. They also bring into the mask shop the data that says, here's the patterns of the chips that we're going to put on the photomask. The data arrives in one of a couple of different file formats. The most popular today is GDS2, but the newer format is OASIS, and that's beginning to become more and more popular with the larger data files. When the data comes in, it's in the form of a layout, a polygon, for example, that maybe it looks like an elbow. We need to fracture it. We need to break it up into primitive patterns. Fracturing takes, say, an elbow and turns it into two jutting rectangles. Depending on the type of writing tool that we are going to use, it may break it up into individual pixels as well. But we now have the format that the writing tool needs to write the patterns on the mask. We also might add test structures, alignment marks, barcodes, and other things required to manage the mask in the mask making process. Then we actually write the patterns on the mask. That will be the subject of lecture 2, the next lecture in our 3-part series on mask making. But we take usually electron beam writer, but for lower resolution mask we might use a laser writer to write the patterns. One way to do that would be to scan a laser beam or scan an electron beam and then blank the beam, turn it on or off where we want the patterns to be or where we don't want a pattern to be. Again, we'll talk about that process in a lot more detail in the next lecture. When we're done writing the mask, we then need to process the resist. We develop the resist just like in a normal lithography process. We can have positive resist and negative resist. There's chemically amplified resist and conventional non-chemically amplified resist. Wide variety of types of resists are used in mask making. When we're done developing, we have our patterns in photoresist. We need to transfer those patterns into the absorber using an etch process. In the old days, we used wet etch, an acid that would etch, say, a chrome material. But today, with our small patterns, we almost always use a dry or plasma etching. Finally, we strip the resist away, and we've got our photomask. We then do some metrology. The main two things we look at are the critical dimensions to make sure that the proper size and within specifications, and the registration and overlay of the patterns. These are the same things we look at when we're printing wafers after a lithography step, but the same errors in the critical dimensions or overlay or registration of the photomask will have a direct impact on those same errors on the wafer. So we got to get it right in the mask first, or we have no hope of getting it right when we print wafers with them. Well, you'd think by now that we'd have a finished mask, right? Well, the answer is in fact no. We have one more important series of things we have to do. We have to inspect for defects. The inspection for defects is something we'll talk about in the third lecture in more detail, but basically we have to guarantee that our photomask is 100% defect free. Any printing defect on the photomask will be disastrous from a yield perspective, so we have to make sure that we have a zero defect mask. We do that with a 100% coverage defect inspection. We do this either die to die or die to database. Remember that most of our masks have more than one chip, more than one die on it. The picture we saw had 6 before. So we can compare an inspection image of one die to an inspection image of a different die to see if there's any differences. Those differences we would call a defect. If we find a defect in this inspection step, then we have to repair it. Well, we can throw the whole mask out and start over, but that's a very inefficient process because it can take a day or so just to write the exposure patterns on the mask. So it's much more effective if we only have a few defects to repair them. So we have specialized repair tools that can either add or remove absorber material as needed. We'll talk about these repair tools in a little bit more detail, not a lot of detail, but a little bit more detail in part 3 of this series on mask making. And finally, when we're done, we inspect again. We can use repair verification tool, something called AIMS, the Aerial Image Simulator tool that it's a microscope that behaves like a stepper or a scanner, so we can see whether our repairs were effective. And we might go ahead and inspect the entire mask again to make sure we didn't add any new defects. When we're done, we have one last step, and that is to apply a pellicle. Again, I'll talk more about pellicles later, but pellicles prevent new defects from being added. But even when we're done adding the pellicle, we have to inspect again. We cannot ship that mask out to the customer unless we are 100% sure that there are no defects on that mask that might print on our wafers. Well, that's the mask making sequence. Let's look at the materials that we use to make these photomasks in a little bit more detail. First, the substrate. Back in the days of G-line and I-line lithography, where we had visible light, 436 nanometer wavelengths, or near UV, the I-line, 365 nanometers, we were able to get away with some fairly simple glass like soda lime glass. That's the kind of glass we use for our plate glass windows in our homes. It's very simple kind of glass, but as the wavelength shrank, we needed more sophisticated materials that transmitted light at these lower wavelengths. So at the deep UV, 248 nanometers or 193 nanometer wavelengths, we have switched to amorphous fused silica. It's a synthetic quartz. Now we call it quartz, but don't be fooled, this is not a crystalline material. Quartz is really a crystal. These aren't quartz. We just, for some reason, we always call them quartz in our industry, but they're amorphous fused silica. For EUV, however, we'll talk about EUV masks in part 3, we actually have a reflective mask rather than a transmissive mask, and we have a non-transmissive low thermal expansion substrate, LTE substrate, with multi-layers of molybdenum and silicon, maybe 50, stacked up to make a reflector, make a mirror out of the EUV mask. Then we add an absorber. For a long, long time, we used almost exclusively chrome as our absorber. Actually, it was chrome with a gradient of chrome oxide. Chrome oxide acts as an anti-reflective coating, and is on the order of 100 nanometers thick. But chrome is kind of hard to etch, especially with a dry etching process. And so we've switched to some other materials that actually work better than chrome. Also, phase shifting masks require some different materials. The attenuated phase shifting mask, a very popular mask, uses molybdenum silicide or molybdenum silicide oxynitrides. They're a little bit thinner, maybe 70 nanometers thick, and they shift the phase of the light. We'll talk about that a little bit more detail in a moment. We also use opaque MOSI. MOSI is molybdenum silicide. Opaque MOSI on glass, or OMOG, is another popular material that replaces chrome. It's opaque like chrome is, but it's a little bit thinner. We can get down to 60 nanometers, and it results in better optical performance to have this thinner rather than thicker material to do our diffracting. We also have some anti-reflective coatings on both sides of the glass and on the chrome itself to minimize reflections. We won't go into any of the details of this. And finally, the specs on our mask blanks as we get them in. Well, certainly the flatness of the mask is a key component. Any flatness variations on the mask will translate into focus errors on the wafer. Also, if we have a phase shifting mask, we have to spec the phase and transmittance of these masks. And there are other things that are important as well. I mentioned that these are 4x masks typically. We have other reduction ratios that we've used over the years. The very early projection tools were all 1x. The next generation of tools was 10x. We've also used 5x, but we've sort of settled on 4x as the best. What are the trade-offs of using a higher or a lower reduction ratio? Why have we picked 4x, for example? Well, one important issue is the printability of defects. If we have a defect that lands on the photomask, any reduction ratio will reduce or shrink the size of the defect that we have as well. Therefore, if I have a higher reduction ratio, here, the right-hand column, then some smaller defect won't print because it'll be shrunk by this higher reduction ratio, whereas maybe that defect would print at a lower reduction ratio. Well, that kind of pushes us to want to use higher reduction ratios in order to get less defect printability. But there's other factors as well. For example, in mask making, if I have to print a feature, well, a higher reduction ratio means the features on the mask are larger. Larger features on the mask are easier to print. It makes the mask making easier if I use a higher reduction ratio. So again, that pushes us to want to make masks with a larger reduction ratio. Defects don't print as easily, and the mask making is easier. But there's a couple of factors that work in the opposite direction. One is the optics of the lens. The larger the reduction ratio, the harder it is to design and manufacture the lens optics. Basically, the mask is getting bigger, and some of the optics have to get bigger as well. In fact, 1x 1x optical systems are the easiest lenses to make. But we don't want 1x for a variety of reasons because of the difficulty of making the mask. Still, we want the reduction ratio to be as small as possible to maintain the ease of lens design and manufacture. Mask uniformity, on the other hand, also pushes us towards the desire to make smaller masks. If you think about it, if I have a 8x magnification instead of a 4x magnification, for example, then my mask is going to be twice as wide in both dimensions. Instead of, say, a 6-inch by 6-inch mask plate, I'd have to have a 12-inch by 12-inch mask plate. These larger physical masks make it harder to get uniformity across the mask. Right? Instead of uniformity across a 6-inch blank, you have to get, or mask, you have to get uniformity across a 12-inch mask, and that's always harder. So you see, we've got a couple of factors that are pushing us towards higher reduction ratios and a couple of factors pushing us towards lower reduction ratios. And the result is we've compromised at about 4x. Is this the best that it could possibly be? Well, maybe, maybe not. But it's probably good enough. It's the industry standard today, and I seriously doubt it's ever going to change, at least not in the near term. Another important idea in the world of masks is that we sometimes want to use phase shifting masks. Our conventional mask, which we call a binary mask or a transmission mask, only modulates the amplitude of the transmitted light. Think of a transparent substrate with absorber patterns. The transparent substrate transmits all the light, and the absorber pattern blocks all the light. So you have binary, 1 or 0. Either light goes through or it doesn't. A chrome-on glass mask is the typical version of that. But light has properties other than just the amplitude. We can also modulate the phase of the mask as it's transmitted. And that's what a phase shifting mask can do. In fact, most phase shifting masks modulate both the amplitude and the phase. We'll talk about the two most popular types of phase shifting masks in a moment, alternating and attenuated phase shifting masks. But first, how do we in fact shift the phase of the light? Well, first of all, phase is a relative quantity. So what we're going to do is shift the phase of the light in one part of the mask relative to the light that's transmitted in a different part of the mask. So here's a mask blank over here. I have light going through it, and it comes out, at a particular phase. Next to it, I have light going through that same blank, but on top of the blank, I pile up a pile of glass, a piece of glass of thickness T. Now, the glass has a refractive index of N. I say typically 1.5. The air has a refractive index of 1. So as the light is transmitted through that thickness of a glass, thickness T, it's undergoing a phase change upon its travel through that glass. Well, the wavelength of light is equivalent to a phase. Every wavelength of light goes through a phase shift of 360 degrees. Right? One wavelength, 360 degree phase change. But inside the glass material, the wavelength is reduced by that factor n. So if lambda is the vacuum wavelength of light, then inside the glass, the wavelength is in fact lambda over n. Well, here I I will result then in a phase shift between these two beams of light, the one that goes through air of thickness T and the one that goes through glass of thickness T. And the phase shift is given by this formula down here. Delta phi is the change in phase, or the difference in phase between these two rays. And you can see that it is 2 pi times the thickness of the glass times the difference of the refractive index between the glass and the air, all divided by the wavelength. If I adjust the thickness just right for any given refractive index, I can get whatever phase shift I want. But the phase shift that I always want is 180 degrees. A pi phase shift means that the light coming through the air is exactly opposite phase, 180 degrees out of phase, with the light going through the glass. What are we going to use this phase shift for? If we can make it by adding some extra glass, for example, what are we going to use this for? Well, I'll show you the phase shift principle by first comparing to a chrome-on glass mask. So the chrome-on glass, or any absorber on glass, is a binary transmitting material. Light going through the glass, we say, has a transmission of 1, so the electric field right at the bottom of the mask will say has a value of 1, and no light makes it through the chrome, so its electric field just going through the mask is 0. So kind of an idealized transmission function is the electric field at the mask. It's 1 or 0, depending on whether we're underneath the chrome or underneath the glass. However, as the light propagates away from the mask and goes through the lens and is imaged onto the wafer, we have diffraction. A simple way of looking at that is some of the light coming through this space is diffracting underneath the chrome pattern, or where the chrome pattern would be on the wafer, and some of the light coming through this space is diffracted and lands on the wafer underneath the chrome line in the middle. The result is an electric field at the wafer that's bigger than 0 because of this diffracted light. That produces an intensity equal to the magnitude of the electric field squared, which is also bigger than 0. This added light degrades the quality of the image and ultimately limits our resolution. What if I took some phase shifting material and added it over one of the spaces? So I put a thickness of glass underneath this right space, exactly enough to produce a 180 degree phase shift of the light compared to the space that doesn't have the glass piled on it. Well, the electric field can be drawn something like this. Still, 100% of the amplitude goes through the shifter, but it's shifted in phase by 180 degrees. We can draw that by saying the electric field has a value of -1 instead of +1. So -1 simply means that electric field is shifted by 180 degrees compared to the +1. Now the electric field at the wafer is going to look something like this, and you see that it has to go through 0. To go from plus to minus electric field, it goes through 0. In other words, the light that's diffracted from one space coming underneath the chrome line in the middle exactly cancels with the 180 degree phase shifted light coming from the other space that diffracts underneath the chrome line, so that I get 0 at the wafer. 0 electric field produces 0 intensity, so now I have a line, a small chrome line that is darker because I have a phase shift on one side of it compared to the other side. That's called an alternating phase shifting mask because we have this 0, 180 degree on the spaces alternating or surrounding that small chrome line. Another style of phase shifting mask is the attenuated phase shifting mask, where we have this molybdenum silicide material that is not 100% opaque. It allows a small amount of light to be transmitted, say 6% of the intensity or 9% or 12% of the intensity is being transmitted compared to 100% that's going through the space. Now, at first you might think that's bad because our features are not as dark as they should be, but I not only adjust the transmittance through this material, but I'm also changing the phase of the light, making it 180 degrees out of phase. So while this is an electric field that's, say, maybe 25% transmitting compared to over here, it is 180 degrees out of phase, so it's a negative 0.25 electric field. that means the electric field passes through zero to go from plus to minus. And when I square the magnitude of the electric field to get the intensity, I have light going to zero. You see what the phase shift does is zero light and 180 degree light, light that's out of phase with each other, combines to make darkness. And we use phase shifting masks to control the darkness and get better quality images. Well, this is just a review of the phase shifting principle, but it says that we have other ways of making masks, ones that require us to make alternating phase shifting masks, and mask making processes that require us to make attenuated phase shifting masks. As we'll see, both the chrome-on glass mask and the attenuated PSM phase shifting mask use the almost identical subtractive patterning process, whereas the alternating phase shifting mask uses a significantly different mask making process. So in the subtractive patterning, chrome-on glass mask, attenuated PSM mask, we begin with the mask blank. We have resist coated on an absorber, coated on our quartz or glass substrate. Then we do our lithography. We're going to talk about the writing step in the next lecture. We expose and develop the photoresist. With this, the resist is an etched mask for an etching. In the old days of larger feature sizes, we would use a wet etch for the chrome, but with smaller feature sizes and with attenuated PSM, we will etch the absorber with a plasma etch process. Once we strip the photoresist away, we now have the patterns that we're looking for. We have a mask. But with an alternating phase shifting mask process, we have another set of steps to go through. In fact, we have another lithography process to perform. We must coat the resist with a second photoresist material, coat the substrate, coat the mask with a second photoresist material. We're coating over the topography of the absorber that we've already patterned in the previous step. So this is something new, right? In the conventional mask making process, we'll often buy the blank with the resist already coated on it. So many mask shops would never have to coat photoresist on their substrates. Well, here, if you're going to use an alternating phase shifting mask process, you must be able to coat photoresist, bake it, have it ready for exposure. Then we do an exposure and develop for a second pattern. But this requires another step, which is new to the alternating shifting mask process. The second exposure to the second set of patterns must be aligned to the previous set of patterns. And that's something that's a little bit new. We then use the resist and the absorber pattern itself as an etch mask to etch the pattern into the quartz. Now, in the previous slides when I talked about how alternating phase shifting masks worked, I showed an extra thickness of glass being deposited. It's easier to make the mask if you etch away the quartz. This does the same thing in the phase shifting principle. We have a difference in the thickness of glass in one region compared to the thickness of glass in another region. And taking away glass is the same as adding glass. You can achieve the same phase shift. We just need to make sure that we etch it at the specific thickness, the specific depth of the etch that we need to give us that 180 degree phase shift. And this is something that's interesting and difficult as well. There's no etch stop layer. There's nothing that will make us stop at the exact right thickness. Instead, we have to carefully control the time of the etch rate and the time, to get to the thickness that we want. And that's not an easy thing to do either. So you can see that with the alternating phase shifting mask process, there's quite a few new steps and extra steps. Additionally, there's extra inspection steps. We're going to talk about mask inspection in our third part of this mask making series. And we would have to do an inspection on the absorber patterns after we've made them and do any repairs that might be needed on the absorber pattern. And then we'll have to do more inspections after we're done with the quartz etch to make sure that that went okay as well. Well, we strip the resist here and we have our phase shifting mask, but there's a few extra complications. Something called phase and intensity imbalance. You know, as we've etched this quartz out to make our phase shifters. In fact, the way light transmits through this etched out region is different than if I don't have an etched out region. In fact, these little corners of the etched region diffract light, and some of that diffracted light gets absorbed by the chrome, and as a result, the light transmitted through the etched region is different, is less than the light transmitted. If I look at the aerial images that hit the wafer, you see it's brighter in the unetched space compared to the etched or phase shifted space. This intensity imbalance causes alignment errors and various other problems, so we need to fix that. We fix it in the mask making process. There's a number of different imbalance solutions that people have tried. A dual trench means we keep the relative difference in the thickness between the shifted and unshifted space the same, but we etch a little bit into both. This helps, doesn't quite solve all the problems. We can do a little undercut on the phase shifted space, the etched space, and that undercut can increase the transmittance a little bit. Or the simplest solution is to bias the phase shifted space a little bit, make it a little bit wider than the other space. Or we'll do some combination of the above. Well, these add extra complications into the mask making process for an alternating phase shifting mask. All right, well, what are the big ideas that we've learned about mask making in this first part of our three-part series? First, mask making is its own lithography challenge. Just like lithography is difficult in semiconductor manufacturing, it's difficult in mask making as well. Only this is not mass production. We're not churning out 5,000 copies of the exact same mask. Every mask is essentially unique. It's a one-off. Plus, every mask must be guaranteed 100% defect-free, something that we don't do in wafer manufacturing as well. So the mask making process is its own challenge. We talked about the trade-offs to optimizing the reduction ratio and found that the 4x, whether it's the exact optimum or not, it's good enough and it's the industry standard. Combine that with a 6-inch plate and we have the way masks are used in semiconductor manufacturing today. Finally, we talked a little bit about phase shifting masks and how phase shifting masks can be used to improve image performance. But we learned that alternating phase shifting masks require a much more complicated mask making process than attenuated phase shifting masks. The attenuated phase shifting mask uses a very similar process to chrome on glass. In fact, the attenuated phase shifting mask with off-axis illumination is quite common, and alternating phase shifting masks are used only rarely. In the next couple of lectures, we'll learn a little bit more about mask making, inspection, repair, and a few other topics as well. Thanks.